In the last video, we focused on the idea of momentum and how you can look at the conservation of momentum for an explosion, a hit and bounce, or a hit and stick sort of collision. Now, in those examples, we were looking at how momentum overall, the total momentum, stayed the same before and after for the entire system that we were looking at. So, all the different parts of that. Well, each individual part is actually changing in its momentum. So, the way that we get a change in momentum is through a property known as impulse, and that is our focus for this particular video. Before we talk about impulse, just a reminder of the equation for momentum. Remember, momentum has the symbol lowercase p. P is equal to mass times velocity. So that is the equation that we'll be using in this video as well. Now, if we want to talk about impulse, a good first step is to review the concept that we looked at a couple videos ago in our energy part of this unit. If you remember what work is the mass, the force times the distance that force is being applied. That will calculate our work. So if I wanted to know the work on this car here, it initially had 0 joules of energy because it wasn't moving. Then this work is applied, 5,000 newtons of force for a distance of 100 meters. I can calculate the work being done. It's just 5,000 newtons times 100 meters to give me 500,000 joules. Well, work has this property that it is adding energy to our system. Or adding energy to this particular object. Now, this car had 0 energy. Then 500,000 joules of work was done on the car. So then that is energy now added to the system to give us a final energy of 500,000 joules. If I wanted to find the velocity here, I know that all of that energy is in the form of kinetic energy. We did not change its position at all to store up energy potentially. So all of this is kinetic energy, or 1/2 mass times velocity squared. If the mass is 2,000 kilograms, the only unknown is velocity, so I can calculate that. That is 22.36 roughly meters per second. So work was our way of adding energy to an object. Impulse has a very similar feel. Impulse is our way of adding momentum to an object. Impulse is calculated instead of force times distance, it is force times time. A very, very similar calculation, but that slight important change. So now, if I look at this example, my initial momentum is 0 kilograms times meters per second because it is not moving yet. If I time how long it takes to do the exact same thing that we looked at, now instead of multiplying the force times the distance, I'm going to multiply the force times the time to find my impulse. 5,000 newtons times 8.94 seconds is roughly 44,700 kilogram meters per second. Don't worry too much about the unit just yet, but my impulse is found by multiplying the force and the time. This impulse adds momentum to the system. So my momentum was initially 0. Impulse is added 44,700, and that gives me a final momentum of 44,700 kilogram meters per second. If I want to calculate the final velocity here, I know that the momentum is mass times velocity, which is 2,000 times v. The only unknown is v. I can solve for that, and I get roughly the same answer that I did solving with work and energy, about 22.35 meters per second. So work can change your energy. Impulse can change your momentum. I mentioned something a little bit ago about the units and how we didn't worry about the units right there. Let's look at the units more specifically now. Because if impulse changes momentum, we need these units to line up. Just like work and energy both had units of joules, impulse and change in momentum should also have similar units. So if I calculate impulse, just taking the force times the time, unit of force is newtons, unit of time is seconds, I get impulse is Newton seconds. Notice this, I do not say newtons per second because it's not newtons divided by seconds, it's newtons times seconds, so I call them Newton seconds. Well, that actually isn't a full those aren't all fundamental units because newtons is a derived unit that can be simplified down to mass times acceleration, or kilograms times meters per second squared. So if I plug that in instead, I get a unit for impulse: kilograms times meters per second squared times seconds again. Seconds divided by seconds squared crosses off a little bit, so I only have 1 second on the bottom. So this turns into kilogram meters per second. Notice how this is the exact same unit as what we used for momentum in the last video. So impulse, force times time, simplifies down to the exact same units as momentum, which is mass times velocity. This equation for impulse shows up in your data booklet actually more than once. We see it down here at the bottom of this subtopic 2.4. The impulse is force times the change in time, and that is equal to your change in momentum. You'll also notice here that this is actually the same equation. It's just solved for force. The force is the change in momentum divided by the change in time. So it's just rearranging that last part. Impulse can be used to either increase or decrease an object's momentum. So if we're looking at this rocket here, a force for a certain amount of time will increase because it starts with an initial velocity of 0 and gets faster. Hitting a golf ball, there's a force imparted over a certain amount of time. If its initial velocity is 0, it's going to increase its momentum. It feels sometimes that hitting a golf ball is an instantaneous thing, but if you looked at it in slow-mo, that golf ball deforms quite a bit and is in contact with the club for a while before it fully leaves the club's surface and no longer has that force. But you can also decrease an object's momentum by bringing it to a stop. So like a catcher catching a baseball or a car running into a wall. Those are both examples of an object's momentum being decreased because of a force being applied over an amount of time. So I want you to look at this animation here. Play this a couple times. And as you're watching this, think, how are these situations the same? What is the same about these? And what is different? All right, so a couple of things that I see as the same is showing that they're both 5 kilograms, so they both have the same mass. It looks like they both have the same velocity as they're coming in. So if they have the same mass and the same velocity, they also have the same momentum. So that's interesting. But notice here, this collision is a little bit different. One comes to a stop. The blue one comes to a stop like right away as soon as it hits the wall. And the green one has that cushion there that slows it down over a longer period of time. So predict for yourself, which one do you think has more force? The blue or the green? What we're going to see, and probably what you know intuitively, is the one running into a pillow is experiencing less force than the one just smacking into the wall. And it has to do with the time of that collision, how long that force was being applied. So that brings us to one of the most important concepts in terms of impulse. And it's, how do we decrease or change the force that's acting on an object? Well, there are a couple different examples of this. So if you have an object that's moving really fast, like a skydiver, and you want them to come to a stop. Now, the most common thing that we do is we use a parachute to slow them down so that that change isn't nearly as abrupt. But say they are moving at full terminal velocity and they don't have a parachute. Well, we have to find a way of softening that blow. So here is an example of a skydiver skydiving into a net without using a parachute at all.
There goes the chutes. Luke is on his own. And the crowd on the ground looking up, they have a visual on him right now. He's in. And he's kicking and moving.
I apologize for my sound cutting out there when I paused the video. I just wanted to point out how small the net was from the point that he was currently at. So this net was able to cushion his blow because it extended the time in which he was colliding. If you imagine yourself like playing catch with an egg or a water balloon, what would you do to try to make it so that the egg or the water balloon doesn't break? Well, you'd probably catch it something like this, where you try to follow it along to extend the amount of time that its force is being applied over. Another great example of this is a crumple zone of a car. A car is designed to crumple. If you found a car that went through a collision and then came out without a scratch and like had the exact same shape, it actually is a less safe car because that impact would take place really, really fast, really abruptly, and not have the ability to crumple and extend the duration of that impact. So we can look at this in terms of the equation as well. If we have two trucks here heading towards different fates, this truck on the top is heading towards a brick wall, the one on the bottom is heading toward a giant haystack. And now both of these trucks have the same mass, and let's assume that they're both traveling at the exact same velocity, so they have the same momentum. And we want them to come to a stop, which means their change in momentum is going to be exactly the same. They're going to lose all of that momentum that they have, and what they have right now is the same. Well, say they come to these different fates. The first one clearly has more problems than the second one. Now let's look at the equation to tell us why. This first one happens over a very short amount of time. That there's no give to that wall, and because of that, experiences a very large force. If my change in momentum is fixed, it's based on how fast it was going initially and what its mass is, it means that the only things that I have to play with are how it's distributed among the force and the time. Well, if that time is really small, the force has to be really big to make up for that so that it multiplies out to that same change in momentum. If we look at the haystack happens over a long period of time with a very small force. And it looks something more like this if we're to play with those variables, that a small force requires a very large amount of time in order for it to multiply out to be your change in momentum. So both of these, really interestingly, have exactly the same impulse. That the impulse is the same as the change in momentum, and that was the same. But what's different is how the impulse is distributed between the different variables. If I multiply them together, they're going to multiply out to the same thing. It's just one has a larger force and smaller time, one has a smaller force and larger time. The result is really important for whoever's driving this truck, though. Even though they have the same impulse, that force is what they're really experiencing there. We can also use impulse to speed something up. A great example of that is a cannon. A cannon is designed to speed up the cannonball as much as possible. And you'll find that it actually matters how long it is. So if we want to find a cannon that is going to produce the largest final velocity, we want a barrel design that's actually longer. Because a longer barrel design means that the explosion here will impart a force as long as it's still in the chamber. Here, the force basically stops once the cannonball leaves the cannon. So the longer it's in the cannon, the longer that explosive force is pushing on the cannonball. So the force is the same in this case, but we're changing the time, and the longer the time is, the larger the impulse and the larger the change in momentum. We can see this in terms of like a marshmallow shooter as well, and this is something that you could do at home if you wanted. You can make a little marshmallow shooter straw by just rolling a piece of paper and taping it, and you can try it in a couple different sizes. So you can have a marshmallow shooter that's short and blow, and you'll accelerate it out so it comes out to a final velocity here. A little bit longer, your force is going to be imparted for a longer time, so you're going to get a larger velocity. And then finally, the longest, you'll have the highest velocity out. And the reason here is that this impulse equation is going to tell us where we're going. This change in momentum, though, we can really think about it in terms of the momentum equation. You're not given this in the data booklet, but you can interpret it this way as well, that the mass of this marshmallow isn't changing here. It's the same force and the same mass. This marshmallow doesn't change its mass, which means the only thing changing about its momentum is its velocity in this case. So the mass stays the same. At the same time, the force is also going to stay roughly the same, assuming that you're blowing with the same amount of force, same air pressure throughout. So if our force is the same and our mass is the same, it means that the time can change the velocity. If we increase the time, we're going to increase the velocity. The larger the barrel, the more time the force is being applied for, and the faster it's going to be moving because it imparted a larger impulse and a larger change in momentum. The last thing that I want to focus on here is what would happen if the force isn't constant. So in that last example, the impulse that was being provided was from a force blowing through a straw where the force is about the same the whole time. But in most collisions, we have a force that looks something like this, where it kind of peaks out, like you first hit the net, and then eventually you'll have the highest force somewhere in the middle, and then it kind of tapers off as you slow to a stop. Well, here, if I want to find the impulse of this graph, this force versus time graph, I'm going to use a similar trick that I did earlier this unit. When I had a force versus displacement graph, I was able to find the work from that by looking at the area under the curve, or area bounded by this graph, because the area here is just the y-axis times the x-axis. And in terms of this one, it was the force times the displacement, which is how I calculate work. Well, you might already see where this is going. This graph is not force versus displacement, it's force versus time. So if I found the area here, the y-axis times the x-axis, force times time, is the same thing that we've been doing here to find the impulse. Impulse is force times time. So if you can find the area here, you can find the impulse. In this case, the area is 1/2 times the base times the height of this triangle. The base is 10, the height is 8. So 1/2 times 8 times 10 is 40 Newton seconds. Or you could use the units of momentum, 40 kilogram meters per second. All right, so I want to give you two different impulse graphs, force versus time graphs here. And I'd like you to tell me which one is larger. Is it red, is it purple, or are they the same? So looking at this example, one experiences more force, but over a shorter period of time. One experiences less force over a longer period of time. I know which one I would want to be. I would want to be the less force. But you'll find out here, if you do the math, 1/2 times the height here, 12, times the base 4 is 24 Newton seconds. 1/2 times 6 times 8 is also 24 Newton seconds. So it takes place over twice the time, but it's half the force, which means that they actually have the exact same impulse. Twice the time, half the force. But they don't experience the same thing. The result is the same. They were moving and then they come to a stop. The change in momentum there, the area is exactly the same. But if we had an egg here, and an egg would crack if it experienced a force larger than this line, I want to do whatever I can to spread out that force to be smaller than this, to be lower than this line. In the past, you may have done an egg drop in a previous life. Really, your goal in an egg drop is to extend the time as much as possible so that it experiences less force because it happened over a larger period of time. You might also recognize a similar sort of graph from the beginning of the COVID pandemic. This idea of to flatten the curve was basically to extend out the time of the pandemic so that the force, the number of cases, never exceeded the limits of the hospital. So you'll see a similar graph in other aspects of life as well. So main takeaways here. You should be able to describe the meaning of impulse and how it is related to the change in momentum. You should be able to conceptually describe how the force, how to decrease the force experienced by collision. Because a collision, you're not actually changing the overall impulse, you're just changing how the force and time interact to multiply to give you that impulse. And then you should be able to determine the impulse of a collision from a force versus time graph. Find the area bounded by that graph to find your impulse.